All right, so why don't we get going so we can not be here too long? Yeah, good idea. Yes. All right, thank you. I used to have a teacher that would say, "Good people, good people." I never felt like she was being earnest, um, but she was a good teacher. So anyway, let's get going. Let's just talk about two things. Maybe we won't get through everything that I wanted to get through today because life is imperfect. I want to talk about one more thing, which is caching, and I guess and write buffering. That turns out to be key for like basic performance levels in file systems. So we'll talk about that briefly. Then I'll just, instead of getting too much into like another lecture topic, which everybody runs out of steam for, what I'll just do is we have another project out, which is, what's it called? Boo. Did I hear boo? Who would boo a project? What's that? No. Don't you want to do P5? Let's vote. I vote yes. 1-0. All at the same time. You still have some weeks left. What are you going to do? Let's say you ended with 4A. Then you'd have like all these weeks where you're literally doing nothing. Oh, other classes, blah, blah, blah. Learn stuff for the exam. Yeah, I'm sure you just study continuously for 2 weeks. That's what it seems like to me. Give it, or everyone just gets 100. Yeah, everyone who's here, right? That's a sad commentary about attendance levels. This is the problem with recording lecture. I used to think people came because they're like they like hearing me speak. They're like, no, I just can't get a recording. So.
Can you imagine retroactively finding out if you'd come that you would have done 100 because you're watching this lecture?
That would be like so. Right now, I say everyone here. It's like Oprah. Everyone gets 100. Yes. If you're here, you just have to sign here, right? Sign your name. Anybody who signs their name right there, they get 100. Okay.
That's a small line for all of us.
Well, that's the problem, and it's already been taken up because I signed it. So, okay. So anyway, not too useful. What I thought I would just do is some questions about 4A, the MapReduce project. It's a highly simplified MapReduce. Hopefully, it's not too painful. So we'll talk about that in a second. So let me just first talk about this first piece, caching and write buffering, and then I'll just take questions. So let's do that, caching. And like I say, write buffering, because it's a little bit different. Okay, let's think about our system that we have available to us right now. We have the machine right here. This machine has inside of it things like a CPU, we'll mark that with a C, and then we have memory, we'll mark that with an M, and then attached to it is some kind of disk, it doesn't matter what, it could be an SSD, it could be a hard drive, it's whatever, it's generally slower, right? It's slow. Memory generally is pretty fast. And depending on the technology, memory can be tens or maybe hundreds of gigabytes per second. Devices tend to be 100 megabytes per second for a hard drive. Maybe with the faster solid-state devices, you can get a few gigabytes per second. But whatever it is, this device is going to be slower than memory, which means to make file systems go fast, you're going to use memory where you can. Now, we know that for file system stuff. Now, we know that already memory has a major user, which is when we're running processes, we're storing pieces of each address space of processes in memory. So we already have the VM system is a client of memory. So if we're thinking about what's going into memory, VM pages are going in there. But now what we're going to do is we're also going to put this file system stuff in there, and those two are going to compete with each other to some extent. Where is that important? Well, it's important on reads for sure. Let's say we're reading, let's say we're doing an open, like we did before. Open slash, A/B/C/D/E.text or something like that for reading. If we're opening a file which has, we have to read the root inode and root data contents. Read A's inode and its data. Read B's inode and its data. Read C's inode and its data. Read D's inode and its data. And finally, just to open it, read E's inode as well. Huge number of reads of inodes and data. And if those directories are full of stuff, we might have to read a lot of directory data blocks in order to just to be able to open the file. That would take forever, many, many reads. But if we cache those things, cache inodes. By the way, I'll generally refer to like the information about the data. Sometimes we call it metadata in a file system. So that's metadata as a generic name. So inodes are one form of file system metadata. We'll cache things like inodes and cache directory data in memory. So that means that the first time you do this open, it's slow. But if you ever open the file again, it's fast because all those inodes and directory data blocks are in memory. On older systems, this is a big problem because older systems didn't have a lot of memory. Modern systems have lots of memory, which means even with pretty large file systems, the small amount of information you need to store, like the file system hierarchy and inodes and directories, almost always going to be in memory, which means it's going to be accessed quickly. So it's super important on reads, like when you're reading just to open a file and doing a path traversal, to have a cache. A second case, so that's open. I guess I'll just mark it. I'll kind of change the way I did this. I'll just call this the reopen of the file. So opening a file, clearly caching is important. Another case, when we're dealing with large files. A large file, if we think about how a large file is laid out, let's pretend this is our disk here. We have, remember, those bitmaps and things like that. Then we have some inodes here. And a large file would, of course, have some direct pointers which point to a few data blocks, maybe like 12 or something like that. It would also, a large file like this would have an indirect block, which I'll color differently. This is an indirect block. That indirect block points to more data blocks. That same inode will have maybe a double indirect block, which we'll again mark differently, orange. A double indirect block. And that double indirect block points to, say, an indirect block, which I guess I should mark in red for consistency. And it points to a bunch of those, which each point to more data blocks. You can get where this is going. Clearly, pretty quickly, I run out of room for all the data blocks of this file system. We have a lot of, and that's just all file system metadata. It's all locations of blocks for this file, right? It's not the data we're pointing to, these are the only ones I marked data. These are all pointing to locations of where there's data, right? So it's indirect block points to data, double indirect block points to indirect blocks, each of which point to data. So if we have to do a read, like a read from a large file, we have to read, might have to read like a double indirect block, kind of the worst case, let's say, and then an indirect block, and then the data itself. So again, caching is going to make this go fast in the common case, because even if we haven't read the data before, we'll have read the indirect block and the double indirect block. So certainly we can cache those. And then finally, of course, we're going to cache the data when we can. So if we read the same block over and over again, the data of that block is going to end up in memory, and we're going to keep it there. And then when we read from that file, the first time it's slow, the second time it's fast. You can just, on your own laptop, you can do this. If you can know how to access the local hard drive or SSD, you can read a file, time how long it takes, and then just do it again. And the second time and then subsequent times, it'll be much, much faster because it'll be in memory as opposed to actually on the device itself. So caching, an obvious way to keep metadata and certainly even data in the file system, from the file system in memory, and avoid going to the slow device. So that's reading. Now writing is a little bit more interesting. Sorry. So here's a very common pattern in a Unix file system. You open a file, whatever, foo for writing, so write only, let's say. Then you write to it, maybe many times. Then you close it. And at this point, very typically, the file system has actually done no I/O to the disk. This is very common. In fact, what it's doing is instead, it's buffering it in memory. So I do a bunch of writes, I close the file. In fact, the process exits, right? Your process is done, and it just has a bunch of stuff in memory. What happens is later in the background, the OS finally writes out this data to the disk. So why is that useful? What are some of the, there's many reasons actually why, but why is that useful? Why does the file system decide to buffer all your writes and then write them later? Yeah.
I would do it if you write from large file.
Yeah, it seems faster, right? It seems faster because your process exits, it's done with all its work, writing and closing the file, and then the I/O is done in the background. Now, if eventually, if you're doing lots and lots of writes, you still have to do those writes, and you have a limited amount of bandwidth in the system. So there's no magic. You're still doing those writes. So it seems faster. It essentially decreases perceived latency of a running program. What else is useful about buffering these writes? Yeah. That's true. So that's we kind of leave it in memory, and then might be read later. Now that's not necessarily a factor of buffering it and writing it later. That's just saying when you write something, keep a copy in memory so that if somebody reads it later, they can read it, right? And even if we forced it to just write when we wrote it, we could still do that, right? We could kind of, and in caching world, how many people have taken like a hardware course before, like a 552 or something like that? So in caching, sometimes people talk about, do you have like a write allocate strategy or a write no allocate strategy, if that sounds familiar? And that's like about whether you're like, when you're writing, do you kind of make a cache entry or do you kind of write around the cache and just write it to the direct source? So this is kind of a write allocate approach. But yeah, we're going to leave it in memory. Subsequent reads might get it. So that's certainly useful. What else? Well, whether we're writing to contiguous blocks has to do with how we do allocation. And we haven't really talked about that yet. But there are still, even if when we're writing like this, it's useful to buffer. Why is it useful to buffer? What else is useful about it? Yeah. Yeah, and maybe that's kind of what you were getting at too. If we can kind of aggregate many, let's say, small writes, let's say they're less than the size of a block, into just one block write. So if we were writing 1 byte at a time. Now, if you're writing to a file system and you're writing 1 byte at a time, you probably don't know what you're doing. So that's like a warning. Like, do I know what I'm doing? There should be like an error that the file system gives you, like E_, you don't know what you're doing. And I've always wanted this. Like, why do systems not fail that way? They should say, please don't do that. Even though it's completely legal, you should at least be warned, this is not a good idea. It's like a warning. But if you're just writing like 1 byte at a time to a file, it means first of all, you're causing a lot of system call overhead. It's a bad idea. And then if you were really forcing those writes to disk, you'd be causing like a read and then a modify and a write and then a read that block again, modify the next byte, write it. If we instead leave that block in memory and just kind of fill the bytes up, then we can write it all at once. And that aggregation, sometimes we call it like a batching effect. So that's another reason we want to just buffer things in memory. There's another, even more reasons. Yeah? Yeah, great. So let's say we overwrite the same block repeatedly. If we do that, if we just kind of say, hey, we're writing this contents of this block, and then we update it in memory into green, then we update it in memory to its final resting state of orange, and then we write it to disk once, we've actually reduced the amount of I/O, right? So this reduces the amount of I/O because we allowed that block to stay in memory, and then we only wrote the final version of it. That's another thing. We can kind of reduce, we can essentially essentially do this kind of I/O reduction because we're essentially deleting the old contents and then updating it new. What's another reason that it's good to buffer things in memory? So many reasons that it's good to buffer writes in memory. What else did we learn about disks? Yeah. Not a wear-out problem, just performance. That's true too. If there's a wear-out problem, which actually is a bigger deal with SSDs, which we will talk about, wear-out could be a problem too. But for disk, we just assume the disk doesn't really affect. It's not really affected by the number of writes. Yeah.
We can optimize
Yeah, disk scheduling. Yes, disk scheduling. Remember, if you give the disk scheduler a lot of writes and then you say do that in the best order, it's going to do crazy seek and rotation optimized writing. It's going to do it in the best order. It would do that as fast as possible. If we just give them one write at a time, you can't. So disk scheduling does better with more writes. And one other reason, which is kind of related to this overwrite reason, is you might do this. Open, write, write, close, and then a short bit later, you delete. So if the file is deleted, then you have this advantage of buffering is that you never had to do a write to disk at all. So you do 0 writes. Unlike is a delete operation, if we don't remember that. So many reasons you want to buffer things in memory. It lowers your perceived latency. It might be read later, so leave it in memory. You can kind of turn many small writes into like a block size write or even bigger writes, maybe a number of writes. If you're overwriting the same block, you just force it to disk once at the end. You get better scheduling. And if the file is deleted sometime after it was created and filled, you don't have to write it at all. Now that's why it's good. Why is this bad? Why is write buffering bad? As opposed to caching, which is just kind of like a strict good. Why is write buffering bad? Yeah. Crash means data loss. This is a big problem. So it's a trade-off. It's basically saying the system assumes your data is important, but not so important that I'm going to write it right this moment. I'll write it in like 30 seconds. So every 30 seconds, I'll wake up and write some stuff to the disk. And if you have data that's really important, you should, if you really care about persistence, about immediate writing, you have to call a different file system interface. In fact, what you do is you call open to open the file, then you do a bunch of writes on a file descriptor, write. And then what you do is you call fsync. And fsync forces this data to disk. And therefore, by definition, it's slow. But it's safe. So that's exposed to people, one second on the question, that's exposed to developers and people who know what they're doing, like you're writing a database that's using the file system of some kind, or you really care about the data in a way, and you want to make sure that you write this thing out to the disk right now, you have to call something explicit. In general, the file system has a very soft guarantee that it'll eventually write something to the disk, but it doesn't do it right away unless you tell it to. And on Mac OS, it doesn't even do that. On Mac OS, fsync's guarantee is weakened because it turned out that there were a bunch of applications got built on Mac OS such that when they called fsync all the time, and they called fsync all the time because they're like, well, actually my data is really important. It made the systems run really slowly, So as good engineers, what did the Mac OS developers do? They changed what fsync meant and made it not force everything all the way to the disk, just flush it out to disk memory, but not disk surface, which makes it run faster, but isn't safe. So on the Mac OS, you have to call F control with a F full sync option in order to get what most people would just think fsync does. So that's a way to be tricky when you're building a file system, is if you don't like what people are doing, just change the meaning of it and put it in the man page. And let's see if that's still true, actually. I'll go here really quickly. What we have is, I haven't looked at this man page in a long time, so I didn't demo this, I didn't dry run this, but let's see if that's true on fsync on my Mac here. Blah, 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 blah. You can see, oh, for applications that require tighter guarantees, we provide this, the full sync F control. The full sync F control actually does what you thought fsync does, is what it should say. So in any case, an exciting man page exploration, which is not complete. Okay, there was a question.
Does it take away from resources for
Yeah, so the question is about the competition between the file system storing its metadata and data in memory versus the VM system, which is storing your process pages in memory. Absolutely, those two are both now competing for the same resource. And so whatever memory management strategy you have has to take that into account and kind of balance the two. In very early systems, they were worried about that, so they would just statically partition memory. They'd say, oh, 10% of memory is used for file system caching and 90% for applications. Over time, people just have moved towards a unified kind of replacement strategy, which will just kind of treat all pages more or less similarly. There's a lot of details to that that I'm not going to get into. But yeah, you have to take those things into account. It could be that when you're reading a lot of file system data, you're forcing process pages out of memory. If you have a lot of process, like heap pages in a process, you might be forcing file system data and metadata out of memory, and those could cause different kinds of performance problems. Other questions? Yeah.
And just that one of the advantages is that if you keep updating the data, you only need to perform like one, right, instead of like multiple. Right?
Yeah.
But what if you want to read the file during that, like between that phase?
Yeah, that's not a problem, right? So the question is about this case where you're overwriting the same block repeatedly, right? So in that case, let's talk about it down here. Like, let's say there's process 1 that's doing writing of a file and process 2 that's doing reading of it. So process 1 does a write to a particular file, and then in memory, we just have like the blue version of that. And then if some process 2 comes along and does a read, it's going to get the blue version of that. And if it does another read over here, it'll still get the blue version. At some point, process 2 decides to do an orange write, and that overwrites this data with orange. Then subsequent reads from process 2 will get the orange data. What you're kind of getting at is there's a concurrency issue which we haven't talked about. When you're reading and writing a file, even across separate processes, there must be some locking going on. We haven't really talked about it. I'm assuming you'll kind of implicitly infer that. Of course, there's concurrency. We have to have locking. The locking here will ensure a serialization of all those reads and writes across the file. So you'll always just get one version or the other of depending, like essentially you can think of the system calls as interleaving in that case. So you'll see either what was before the write or after the write, and repeatedly that happens over and over again. First, then we get the orange, then we overwrite it again. Process 1 overwrites it and it becomes red, and then we finally write that to disk, and whoever reads it will still see the in-memory version, which is red, but then also on the disk there will be a red version at that point, and we'll only have written to disk in that case. So the right thing will happen in that case of write. Okay. Right. Yeah, yeah. So that's a great question, and I kind of implicitly assume that you would understand how I think it works or how it works, but I didn't say how it works. So the file system cache is by definition shared. Thank you for asking that. I don't know why I never say that in class, but it's implicit in what everything I've said. It's shared across all processes. So that's not a per process thing. My pages in my address space, when I read something into my page in my address space, that's mine. But the file system is this shared thing. All the processes are accessing it. All the metadata, when we're talking about caching, all that's shared. And so when somebody writes to it and then somebody else reads from it, They're just talking about the same block. There's no like per process file cache. There's just one. Thanks for asking that. I don't know why I didn't explain that. I guess it's because I'm a lousy teacher. It's a sad story. Always realizing things you don't explain, and it really makes me feel sad. Now I'll go home and feel sad. So thanks for that. Yeah, that's how I improve. Feel sad for a while. So great. Other questions? Yeah. I don't quite understand the question. On the Mac, what the question was like, why are Macs so awesome? I don't know. They just really are. I get no money from Apple, so this is not a paid advertisement. Your question was, I didn't understand it. Oh, yeah. Okay, got you. Okay, so what the stupid Mac fsync does is here is the drive. The drive is actually like the spinning platters and all that stuff, right? So remember we talked about there's a spindle and there's all these circular rotating things. That's like the persistent surface you have to record things on so that when power goes away, you can still get it. But in the drive, there is also a little bit of DRAM. Not very much, 8, 16, 32 megabytes, something like that. This is drive DRAM. So when you do from the host, here's the host, which is now somehow a tiny host, much smaller than the hard drive because I ran out of room. There's host memory, and there's like, this is gigabytes and gigabytes of memory, right? So this is strangely smaller in my picture, but much bigger in reality. So when you write something to host memory, you buffer it here. I'm going to change the color of that. So it's like, here's this red block I have here. Then when we first write it to the disk, it's going to drive DRAM, and then the drive eventually is going to write it to like the drive surface. Let's say it's some partial write around this track or something like that. What the Mac fsync is, what a normal fsync would do, is all these steps, right? You would write it here, then you'd fsync it to here, and it would wait for it to be written down here, and then tell you it's done. And what Mac fsync is doing is saying, you know what, we're going to write it down here and tell you it's done. That's kind of enough. Right? Because what that does is, what case does that help you with? There's a case that's really good with helping. It actually does improve like durability in some cases. What bad thing could happen at this point now that the drive has this this block and it's okay? Like what bad thing could happen? Like if the OS crashes or something about the OS, like on the host side something bad happens, the drive still has it and the drive will write it to its surface. The problem you have is the drive, if it loses power at that point and isn't able to flush all of its DRAM to this disk surface, that's when you have a problem. So it does kind of improve things, but it doesn't get you all the way to waiting for it to really be persistent and therefore durable across crashes or power losses. Drives, in fact, generally when they lose power do try to write a little bit more, but they usually just have enough in order to guarantee that if you're doing a 512 byte write, that it'll complete before power runs out. So it'll be like, ooh, it's like it's slowing down, but it can do one last 512 byte write, and that's how it guarantees 512 byte writes are atomic. That's the minimal unit of update to a hard drive. And yes, I will edit the video to remove that sound effect that I just did, which has nothing to do with hard drive. It's just a sound effect. Other questions? Good question. Sorry, I didn't explain that in much detail. The man page of the Mac. Yeah. All right. Okay, so why don't we do this? Let's actually take an official break, and then I'll just take questions on the MapReduce piece. So if you want to talk about that, great. If you feel like you're good on the MapReduce piece, you can leave. If you love MapReduce, you can come to the front, etc.